In this video, we're going to introduce a new option for graphical checking in Adapt Builder 2020 called the Integrity Check for Design Sections. This option can be found after we design the sections if we use the result display settings or the result browser, and we go here to Analysis. Under Design Sections Investigation, there's a new option here called Idealized Section Integrity Check. And under Display, we can set the threshold, the criteria. So here it's set to 25%. And to begin, we're going to outline what the definition of a physical section is versus an idealized section. When we pass the design sections over to the designer in the program, the tool that actually designs the reinforcement and evaluates the design cuts, the program parameterizes different dimensions or geometric properties of a section that can then be absorbed and handled by that designer. So we have a thing called a physical design section and also an idealized design section. So in this case, we have beam sections. We're going to take a look at the beams in the body or the field of this slab. And I'll go ahead and just turn on the X direction, and we'll look at a midspan condition of a T-beam. And we can see this section dialog, this property dialog, shows us two images. One is called the physical section, and this also shows the base reinforcement and any tendons in the slab or the beam. And also the design section, which is idealized with the calculated rebar. So this section, if I blow this up by double clicking, we have the two sections. Anytime you have a T-beam that has no depressions in slabs and the design cut doesn't extend through multiple slabs, or even a flat slab, but let's say it's a two-way flat slab, and there are no drop caps, no drop panels, no slab depressions, etc., we usually get 100% compatibility or 100% accuracy in terms of checking the integrity of the physical section versus the idealized section. And what that means is that the properties of this section 100% equal the properties of this idealized section, which is being used again to calculate reinforcement, stresses, top and bottom, extreme fiber stresses, pre-compression, especially for post-tension type systems. If a user was to open the details of this section, we can see that the program now reports different options here: physical section properties, idealized section properties, and the percent difference. This percent difference is checked in two important section properties. One is the area, which is used to calculate pre-compression. The other is the moment of inertia, which is used to calculate the stresses, and also this affects, for example, or gives you an indirect check of, let's say, accuracy level when the program calculates reinforcement based on some section that's composed of concrete and reinforcement and is of some shape. So this percent difference is essentially zero in this case, where the physical section equals the idealized section. Now, if I was to go and turn this check on, we can see that the physical and the idealized shape here is almost all less than 25%. I can double click on any section cut, I can go to details, and you can see that percent difference. Now we're going to move up a level to level 3 in this model, and there's some difference in the way that the slabs are modeled with respect to beams and depressions and offsets. Let's go ahead and just clean this up a bit. I'll turn off the design cuts for a moment, and we're going to take a look at this area right here. And if we look at this area, we can see that the main slab is 10 inches, has 0-inch offset. There's a beam passing through the slab. Right here, there's this beam, and that beam is also offset down. If we look at that beam is offset by 2 inches. Positive value here indicates downward. There's one other slab here, this little depressed slab. That is a, let's go back and select the properties of that slab. Let me select it one more time. This is an 8-inch slab and it's set down 2 inches. So if I was to take just a cut through there, if I go to visibility and use a section cut tool, I can observe the section. This is a fairly unique section. It's basically a spandrel section with a tiny location where it's depressed. So it's nothing crazy, but it is something unique as compared to what we were looking at previous. It's even unique compared to a section here, where this is a pure spandrel section. And if I was to then generate my design cuts, we're going to go back and let's go ahead and just remove those two sections. Let's generate the design cuts along these spans. Okay, and I want to focus on this area. These are symmetric. This area here is very similar to this area. You'll notice a difference here, and we're going to talk about this difference. We have two support lanes. We have one support lane passing through the beam. We have another one on the outside of that depressed area, and that's really a modification that we made in order to clean up these regions and to provide more accuracy in the results. So if I go through and I design the sections for this level, let's do that. We're going to go and design the sections. And I'll select yes to save those designs. And then I'll go through and we're going to check the idealized section integrity against the 25%. And we can see there's several design cuts that don't pass. If I look at the other direction, there's just a handful that don't pass. And we come back to this location here and we say, okay, let me double click on one of these design cuts. We have that same physical cut versus the idealized cut. And what happens here is the program takes this this beam and it shifts it to the vertical center line of the section. So we can calculate these different section properties based on the parameters that we talked about earlier. In this case, what's happening is some of the slab here is being displaced. So as this shifts over and we have this depression, the total length of the slab equals the depressed dimension, which is 2 inches. And so this leads to a fairly inaccurate section when we compare the idealized section versus the physical section. If we look at a section outside this zone where we don't have that depression, we can see this is pretty faithful to the physical section. Even though we translate this over into the center line position, if we look at the details, the difference is 0. If you were to calculate the moment of inertia bending about an axis along the global x-axis in this case, the percent difference is 0. And so we get very little difference in if we were to evaluate both for the calculation of rebar and the calculation of stress. Back over here in the problem area, if I look at the percent difference, it's 42% for the area. The moment of inertia is actually 0%, but the area is 42% difference. So that flags this section. And we say, well, how can we revise this to make this more accurate with the design? So what we've done is we had that same situation here, and all we've done is we've tried to separate these two locations. So I put a support line for the X direction here, and I'll just trace that so you can see where we start and end that. It basically follows the length of that depressed region. And I've also added one other key element here, and that's called a splitter. And I'll turn the splitter on from the strip results visibility. This is under the floor design ribbon, and I'll turn the X splitter on. This splitter is just a boundary. It tells the program stop that design strip from cutting into that location beyond the splitter. And we end up with these two strips. So one strip, this strip is now just a flat slab. The other strip that we see here is a spandrel T-beam. This strip essentially looks like out here we're just cutting the flange back so that it doesn't extend into a zone of two different thicknesses. It's important for a user, if you have really complex geometry in a slab, to make this check for idealized section integrity. You can flag and determine where you might have issues and how to proceed with those issues. If you have any questions about this new feature, please contact us at adaptsupport@risa.com.